Hi, my name's Stephen Kaplan, and this is my MAE 535 demo project. Today I'll be talking to you about linear motors. Linear motors impact our lives on a daily basis and are used in a variety of applications including high-speed trains, railguns, and automatic sliding door systems. I was intrigued by the potential use of a linear drive system for an automatic sliding door when I noticed a technician servicing a belt and pulley driven sliding door in my building. The goal of my project was to build and test an automatic sliding door assembly which replaces the older belt pulley driven systems with a linear motor. Let's discuss the theory behind linear motors. Some use DC current, AC current, or no current at all, and propulsion is achieved by way of permanent magnets. By far, the most common linear motor is known as the linear induction motor, which uses three-phase AC current to drive an alternating magnetic field. The stator, also referred to as the primary, is usually attached to the moving object and consists of copper windings around a permeable iron core. The rotor, also called the secondary, is usually a flat metal sheet or an alternating permanent magnet array as seen in this picture. The three-phase alternating current provides propulsion for the device. Continuously switching the poles of the electromagnets contained within the primary at a frequency of 50 Hz induces attractive forces for the leading magnet and repelling forces for the trailing magnet. Let's look at a few of Maxwell's equations to understand how electromagnets generate a magnetic force. Biot-Savart's law states that a current-carrying conductor within magnitude and direction will produce a magnetic field. This equation lets us calculate the magnetic field intensity H anywhere along an infinite length current-carrying conductor. We also know that neighboring current-carrying conductors will generate a force on each other. To calculate, first you find B, the magnetic flux density produced by another conductor, and then apply that to the force relationship equation. This equation is very similar to the Lorentz force law, which states that a charged particle moving through both an electric and magnetic field will experience a resultant force. I started by designing and prototyping the mechanical assembly for the door using spare materials in my shop. The concept for the motor was to use the attractive force of the electromagnets, which were mounted in close proximity to a ferromagnetic material. The electromagnets would be turned on sequentially and provide the propulsion for the door. Once it reached the end, the sequence would reverse. Since DC current does not alternate, the switching on and off of the electromagnets would have to be done programmatically through a microprocessor. The prototype was finished, and it was time to begin working on the circuit. I ordered electromagnets that were rated for 50 newtons. I quickly learned that although they were strong, they did not exhibit the fringing effect I needed. They had minimal attractive forces at distances greater than 8 millimeters, but held a strong force when attached. I looked inside and noticed the wire used was 32 gauge, thereby reducing the amount of current and magnetic flux produced. These didn't work for my current build, but it seemed the limiting factor was the distance from the moving object to the electromagnet. I decided to test this relationship. I attached permanent magnets to a steel plate such that all the poles were facing the same direction. I positioned a ferromagnetic target on two adjacent rails allowing free motion and a low friction surface. I first attached a single layer of magnets and then a double layer, thereby reducing the working distance by half. I ensured the fixture was level. When I applied the magnets to the base, the object oscillated back and forth due to the presence of the magnetic field. Two electromagnets were attached to the ends and wired to switches so that the moving object would be stopped on every pass. I confirmed my theory by measuring the velocity of the moving object using a non-contact laser displacement sensor. The chart shows the object moving to and from the sensor. The higher velocity curve occurred when two magnets were stacked. It's interesting to see that the working distance reduced by half and the velocity doubled, thereby confirming the closer the moving object is to the higher density field lines, the more attractive force it has on the object. Future work will include reducing the gap separation between stator and rotor and choosing a more suitable electromagnet with greater flux density and more surface area so that the higher friction and heavier weight door assembly can move using the same forces demonstrated. I hope you enjoyed. If you have any questions or suggestions, please leave in the comments below.